Hi, in this video, we're going to take a look at preparing our data for supervised learning, specifically a regression target variable. Okay, so first thing I want you to understand is that when I'm doing supervised learning, the earlier a step is in my process, the more important it is. Okay, so think about this for a moment. We're going to fit a model, our final model. And that before that, we're going to be like doing our parameter tuning. Before that, we're going to be doing, model fitting, model selection. Before that, we're going to be doing our feature selection. Before that, we're going to be doing our data prep. Before that, we're going to be doing our data collection, and well, actually our data accumulation. Then before that, data collection. And then before that is going to be experimental design. How are we actually going to collect our data in our game plan? Okay, so if I have the ability to, the most important step in my entire supervised learning process is going to be data quality, and that's going to be our study design, our experimental design, our process of collecting the data. If I get crap data in the beginning, there is nothing I can do down the road to overcome that. That's just an aspect of it. We're stuck with it, deal with it. All right, so after that will be the actual data collection. So if things in data collection go wrong, there's nothing I can do about it. I'm stuck with it. You can do things to make things less bad, but it's better just to have good data throughout. Now, data prep is usually where the data scientist actually steps in most organizations. All right, so most of the time you're going to get a project and they're going to want a supervised learning model, either because they want predictions, they want to understand what's going on using a model, or maybe we're talking about like an assembly line process where we want levers to see how we can control the output of something. Those are the major uses of supervised learning. Okay, so most of the time as a data scientist, when I step in, I'm going to be going to a database and just whatever database, whatever is in the schema and tables, that's what I've got to work with. And so experimental design is not on the table, data collection is not on the table. Aggregating the data, bringing it all together to a usable flat file format, that will be in my lane. But when the first step for like real data science kicks off when we're doing our data prep. So this is our first opportunity to make things go the right way. If I make poor choices in my data prep, I'm probably not going to have a good model. Now, there are situations where if you're handed 4 aces, it's nearly impossible to lose. All you have to do is not screw it up. Data prep potentially could screw that up. Also, if you get dealt, a junk hand in poker, there's not really a whole lot you can do to overcome it. So if you have poor quality data, data prep can make the situation less bad, but you're not going to be able to overcome it. All right, so let's get into it. We're going to look at the house prices advanced regression techniques data set from Kaggle. Here's the website that I got. And I'm just going to work through and just show how I would choose to work on this if I was working on a real life project. All right, so I'm going to load my data. So the data set is provided as train and test, and I'm going to row bind the two together. Okay, so my data prep is going to follow 2 different approaches depending on if I know the data that I'm going to make predictions on. This situation, I know what data I'm going to be making predictions on, so I choose. This contradicts the validation test, paradigm for partitioning the data of unseen data, but I find that this actually gives better results for the actual model. All right, so what I'm going to do, I am going to take all of my predictor variables, whether they're train or test, and I'm going to stack them all together into one data frame. And then as I do my data prep on my predictor variables, not on my target variable, I'm going to go through and just run through and use the entire data set. Why am I doing this? Well, this sets it up so that the data that I'm going to be making predictions on has input on the actual data prep. And so remember, my goal is not to have a good model on the training set. My goal is to have a good model on the test set. And this will help like set up things to be a little bit more natural for the test data, which is what I actually care about. So here, when I say test, this is the data that I would be actually making predictions on. So when I worked at the school district, this is similar to, I took last year's data to build a model, and I would go and make predictions on this year's students so that I would anticipate how they were going to perform on ACT, SAT, state tests, things like that. And so I knew all the students that I was going to make predictions on, and I had all the data, in my training set. So I put them together to try and get a better model overall. Now, this is very different than if I don't see the data I'm going to be making predictions on. So let's say that I'm going to build a model, and then next month I need to make a prediction with that model. And the next month after that, I make a prediction. Next month after that, I keep on making predictions. In that situation, I don't have my score data set. I don't have the data that I'm going to be making predictions on. And so because of that, I would not be using that data. I can't use that data at all. In that situation, I would actually partition my data as the data I have to build with, and to train test only data prep on train. And then when I do my validations, my test statistics, I would use the test data. Now, in that situation, my data prep would actually be part of my model building. So I could choose different methods of data prep as part of the predictors that go into my models. And so then I'd have a combination of data prep and model structure and parameters to choose among all the different models when I choose my final model. That's a lot more complicated. If you have the advantage of seeing your prediction data, your score data from the beginning, I feel like you should use it. There are definitely people who disagree with me. Do whatever your supervisor says you should do. Okay, so here I'm going to get NumPy and Pandas in because I'm going to be using those for sure if I'm using Python. I'm going to load my data, just reading the CSVs. Now, you'll notice that I go through and I just load everything as a string right out the gate. This is not the fastest way to go. A faster way to go would be to specify the data type of every single column. This will be a faster way to load my data. Now, it will actually be faster to say do string 100% or to specify each one rather than what I'm doing here. What I'm doing, what I'm doing here is faster than having no parameter at all. By having no parameter at all, I would have set it up so that Pandas has to figure out the data type. Now, the reason why I don't like that is because of things like ID numbers. Let's say social security number. If I have social security number on a column, that's all digits. Pandas is going to think that that's a number, and it would make sense to do, addition, multiplication, subtraction, things like that. That's not the right type of data for that. So I would rather have that loaded as an object or a string. And so I'm having everything loaded as a string, and then I'm going to go in and set up that my numerics are going to get converted over to numeric value in a moment. All right, now I'm going to go through and make sure that my partition is preserved. Now, on my test data, I don't have the target variable because it's the test data. So I'm going to just say, hey, this is all, not a number. And then I'm going to concatenate. So here I'm going to row bind the data. And so the axis is 0, which is the default setting that's saying that I'm binding by row. So remember, when we talk about data frames, matrices, and two-dimensional arrays, dimensions are always rows before columns. And so the default is axis 0. 0 corresponds to rows. Now, what I'm doing here, I'm imputing everything with an NA. Now, what is this going to do? Every time I have a categorical value, I'm going to have an NA, and that's going to be a level for representing missing values in my categorical data. I feel like this is a good choice. But wait, there's more. You'll notice that I do n/a like this. Why do I do that? That's how Excel handles missing values. And I find that stakeholders definitely have worked with Excel, so they've seen the n/a. They're going to be more receptive to seeing that when I do my visualizations and my presentations. All right, so now I'm going to convert the target variable, which is sale price, to a numeric. And you'll notice I'm going to coerce it so that if there's anything that can't be converted to a number, it's just going to be forced into a missing value. And so boom, I got it. And now during my data exploration before the video, I saw the pool area is a meaningless column. I got rid of it. And now here is the tail of the data. So here we can see, that I've got sale price is not a number. And here's my partition column. So I have that preserved. And I can see my range of, predictor variables. I also have the ID column here. Okay, so now something that I do professionally is that when I'm working on a project, I will group my variables by data type and by how I'm going to use them. So I'm going to have a column for I will have a list for all of my target variable names, and I'll have a list for my categorical predictors. I'll have a list for my numeric predictors. I'll have a list for all my date column names. I'll have a list for all my ID column names. Let's see what else. I'll usually have an other and a drop. And so one thing that I'll do when I have all of these columns, every single column will appear in at least one list. I didn't technically do that here because ID would be in what I would normally call list underscore target. Sorry, ID, list underscore ID would be the ID. Sales price would be list underscore target. And train test would be list underscore other if I was working on a project at work. And so why do I do this? Well, this sets it up so I can easily write for loops to go through and do my data prep. Otherwise, I would have to write code for each one of these. I don't want to do that. I'm lazy. I want to do this quick and easy. So for my categorical data, I'm going to go, these are all categorical predictor variables. So the utility is predictor variable, data type is categorical. I'm going to handle these most of the time in a consistent manner. Also, frequently I'll have a binary, a list of all the binary 2-level ones. Now, for numeric, I'm going to do data prep differently on these guys, so I've got them in a different list. All right, so let's go ahead and visualize our target variable. So I can see that I have positive values, so no zeros, and it's skew right, and it's unimodal. Okay, so just some interesting information about this. This is definitely not current house prices. I can tell you that, at least not in the Orlando area. Yeah, $1 million is nothing for a house now. All right, so now let's go ahead and sort categorical data by the frequency. So I'm going to go in to each individual categorical predictor variable, and I'm going to sort the levels by frequency. I find that this makes it easier to interpret my visualizations and what's going on. The default order would be alphabetical. Now, another good way to order things would be by the natural ordering. If I had high, medium, low, which is applicable in some of this data, but I'm going to gloss over the ordinal data, honestly. And another way would be to order by the average of the target variable. Typically, I do a mixture of target variable and frequency in my visualizations to show you what's up. That'll come up in a moment. But here I'm saying that I want first to be the biggest frequency values, the ones that have the largest count, down to the ones with the lowest count. And why do I do this? This makes it easier to interpret what's going on. That I see the first one's like the biggest bite of the apple. The highest portion of the data is going to be first and second highest, third, and down the list like that. So as I'm working through, it's quicker and easier to figure out things, and this helps a lot on the visualizations. All right, now, so this was sorting the levels within a categorical predictor variable. Now I'm going to sort the predictor variables themselves by their relationship with the target variable. Okay, so what I'm going to do is I've got categorical data and I have a numeric target, and I want to some way, just as an initial look at, this isn't set in stone, but I want some way to say this variable looks like it's going to be more useful. This one is going to be, second most useful, third most, all the way down to least useful as an initial run. Why do I do this? This sets it up so that when I do my feature selection, it will be much easier to figure out who should I kick out, who should I keep, because I have an order on it. The ones that are coming up first are the ones I probably want to keep. Ones coming up last are probably ones I'm going to get rid of. you know. Now, this is not set in stone. My feature selection process will be more complicated. I'm going to be doing, variable clustering along the way to figure out what's going on. Now, something about this is that I've got numeric. So how I'm going to proceed is that I'm going to do Vigentile binning of my target variable. So I'm going to do quantile cutting into 20 groups. Where I work, we do 20. I feel like 20 is a lot, but I've kind of gotten used to it from doing it over and over. I would personally go to 10, but I've done it enough times that I'm just kind of used to it at this point. So I'm doing Vigentiles. So just 20. And now here what I'm going to do after I've got, I'm binning my target variable into 20 subgroups, subintervals of approximately equal counts, because it's quantile. And then I'm going to use Kramer's V to decide which one is most associated with the target variable and which one is least associated. And so after I do this, so here I'm using the association function from SciPy. And so here I have a contingency table that I'm using. I'm saying method is Kramer's, and I'm doing over the entire list. So here's an example of why it's so nice to have all of your categorical predictor variables in one object. And now I'm going to go through and sort the values. Notice that I'm using the zip function to do the sorting, and I'm only taking the second slot of the sorted aspect. And boom, I've got it. So it looks like external quality is most related to sale price, then kitchen quality, central air, basement quality, garage finish, fireplace quality, garage type. And we can keep on scrolling down. Looks like utilities and pool quality, condition 2, miscellaneous features are going to be the least associated with sales price. All right, so let's work through this some more. All right, so now I did initial setup for my categorical data. Let's go on to our numeric data. All right, so I'm going to go through and I'm going to convert it all over to numeric values. Remember that I loaded everything as a character string just so I could be lazy and not have to deal with it. And since I put in those n/a's, I'm going to have to do coerce to force it to be a numeric. Now I want to go through, I'm going to do a correlation. I'm using Pearson's correlation to check to see which ones look like they're the most related to or have the strongest association with sales price. Well, we have ground living area, garage cars, garage area look like they have the strongest correlation with sales price. And the ones that are at the end are going to be basement, fin SF2, basement half bath, and miscellaneous values. Now, these could possibly be negatively correlated, and they would end up on the end of that. So to do a deal with that, remember, I put in the absolute value. So here, these are the smallest correlation. So for this purpose, I don't care if correlation is positive or negative. So like a large -1, correlation would be highly informative for a predictive model. So therefore, a -1, I would want to have like early on in the list. So with the correlation absolute value, I know that these have a stronger Pearson correlation. These have a weaker, but I don't know what the sign is. But frankly, I don't care. I just want to know which ones have the strongest association measurement. All right, now I'm going to go through and impute the missing values of my new numeric variables. Now, previously, I imputed all of my categorical data with the n/a. I made a new level for those in my data set. And so that handles imputation on that front. I'm good. I'm done with that. For the numeric predictor variables, I'm going to choose to do median imputation. All right. Typically, most of the time, people do mean imputation. Well, if I have skewed data, I should use median. If I have symmetric data, the mean and median are pretty close. So I feel like you should just use median. It's just a simpler way. That way I don't have to check skewness. Now, you'll notice that on this step here, I'm creating an imputation function. In fact, I'm creating an object so that I can do imputation on future objects using this. So I can impute future unseen data. This is important for pipelines. This is a flaw in R. R does not do this as well unless you're using the preprocess function in caret. All right, so here I'm able to transform the data. So notice that when I did this fit, I didn't, at no point did I actually overwrite my data. It isn't until I use the transform on the simple imputer median that I actually transform my data. All right, now at this point, I'm going to go ahead and copy my data just so I can start playing around and exploring some things. Now I'm going to bend the numeric data into widget tiles. I'm doing this next step for visualizations. Your data visualizations can make or break your project by a lot. Good data visualizations help us understand our data, expose contradictions to established beliefs. That's been a big part of my career. Guide us on data prep, and good visualizations build stakeholder confidence. If you don't have stakeholder confidence, there's no point in doing what you're doing. You want to always be building stakeholder confidence. Communication is the most important part of your data job, because if you don't have good communication, your work is going to get thrown into the bin and you're never going to see any fruits of your labor. So here, I'm going to bend my numeric predictor variables by quantiles once again. So in fact, it's going to be widget tiles. Now here, it's going to work out that, maybe there's only three distinct values. Maybe there's a 0, 1, or a 2, and that's it in the data set. Well, when I do widget tiles, it's not possible to get 20 subintervals. There's no way to do that. So I'm going to say duplicates equals drop, and precision equals 0 is for me to just say, hey, don't go crazy on significant digits. Just cut it off. All right, so I'm going to go through, and now I'm going to build some plots. Now, what I'm going to do is that along the x-axis is the bin of a numeric variable or the value of the categorical variable. And I'm going to have numerics in their natural order. Categorical will be ordered from largest to smallest in frequency. And then on top of the bar plots, I'm going to have a line indicating the average target variable value for each of the bins. And so what this does, this is basically a two-way ANOVA visualization that I'm checking to see where do I have differences in my target variable. So what I want to see highs and lows, and I want to see it in a very easy to detect pattern. I don't want it to be like random on the numerics. It can look like craziness for categorical, that's fine. But when it comes to numerics, I want to see an easy to identify trend. And let's see, yeah, let me scroll down a little bit so you can just see how I did this. And all right, so now let's take a look at what the visualizations look like. All right, so I ordered my numerics by Pearson correlation. I ordered the categoricals by Kramer's V. So the first ones that appear are the ones that by those metrics are going to be the most important. And so here is my ground living area. Now you can see that since I did quantile binning, each bin has approximately the same number of observations. And you can see a very nice trend as ground living area increases, we see a strong trend for sales price to increase. All right, that's reassuring. Now we have the sales price by garage cars. And so we can see the difference on each of these. So it's going up, and then it actually goes down. But this is a very small proportion of our data. And so if I think from an ANOVA point of view, well, this is kind of a low frequency bin. It's not as important as this overall trend I see over here. All right, and so once again, we see overall a trend, but then like a dip at the end. But this is higher than most of the data points. And we see a very nice trend for total basement SF. Nice trend for first floor SF. We see a trend for full bath, number of full baths. Total rooms above ground, very solid looking line. Oh, now something with quantile binning. Quantile binning does a better job of making sure that I have enough data points in each subinterval. If I was to do regular interval binning where I chop up into like equal width intervals, what will usually happen when I have a skew right data, which I do with almost every financial project that you work on, I'm going to have some very sparse low count intervals. And when I look at the averages, I can't, I have to first interpret, do I have enough data to trust that average before I can even look at the value of it? Because if there's too few data points, I can't trust the average as an estimate. So I like to use quantile binning because it sets it up so that almost always I can at least trust my averages as I work through the project. All right, so total rooms above ground. We see year built. Going through this. And you'll notice that I do not have a constant width. Like here, there are, this is just 1 year, while this is 2008, 2009, 2010. So, different number of years, but it is working to have approximately equal number of observations in each bin as I go. This dip is interesting. For 1970 to 1973, huh? All right, so year remodeled. Oh, well, look at that. So there is a break in here. Kind of interesting. Have no nothing going on, huh? And so once again, something weird going on in the 70s, but this was a little bit after what we saw before. So this is garage year built. And, so in a real life project, I'm going to first start with the most interesting plots first, and I'm going to keep on working through until either my stakeholders lose interest, while I look in their eyes and I see they're no longer interested, or I start getting to the plots that aren't interesting. So if I keep on scrolling, you'll start to notice that the trend starts looking worse and worse. Like it's still overall increasing, but as I get going, let's see if we can. It starts looking like an earthquake. It becomes harder and harder to interpret any kind of reasonable trend. And so, I wouldn't even show these to my stakeholders if I could. I would usually put them in like an appendix of my presentation so that they could see it if they wanted to. But what I'm actually showing my stakeholders, especially my big boss, is I only show the ones that have like have impact in them. All right, so let's go ahead and scroll down. And you'll notice that when I see weird things like this, I would want to go back and double check some things on these columns for my data prep. Like here, I only see 2 groups. I mean, that's what's going on there. All right, now we're to categorical. And so here, external quality. So I have excellent, fair, good, and TA. So you'll notice that the lowest average is fair, then TA, good, excellent. There's a data dictionary that comes with this data in Kaggle. I believe TA is like it doesn't really belong with this order at all. So we can see that in our test set, we have a missing value going on here. And so we have fair, TA, good, excellent is the order or the target variable. And so yes and no, all right. And so let's see, NA, fair, TA, good, excellent. And so things are going in the order that we would anticipate them. And so, we just keep on going. And, I would give this presentation, if I was giving a presentation, you'll notice that poor, so it goes what? Poor, NA, I'm going vertically on the red dots. Poor, NA, fair, TA, good, excellent. That makes sense. And as I go, lower down, it starts to like not really make sense at times. And I just want to show this to my stakeholders. So I'm getting where Kramer's V is less informative as I scroll down, or there's less of a Kramer's V metric for association as I scroll down. And I would just, present what I want to present to my stakeholders. Don't show your stakeholders anything you don't want them to see. All right, so let's go ahead and start transforming our data. All right, so when I go through and do my visualizations, one thing I'm going to be using them for is for data prep to help guide me on what should I do, how should I handle this? Should this just be converted to a binary variable? How should I group my categoricals? Like, my data visualizations, when I go line by line, individual one, I look at the visualization and I decide how to choose it, assuming that I don't have so many that I have to automate it. So like if I had 200 predictor variables, like the current project I'm on right now, I have 122. I would go picture by picture, deciding how to do the transformation. Here, I'm going to automate it with code because this is just a YouTube video. I'm not going to lose my job if things don't work out. All right, so I'm going to start with categorical data. Categorical data, our number one tool for data prep is binning. All right, I do not want sparse variables as predictors. Sparse variables slow down the system and make me prone to overfitting. The more predictor variables I have, the more prone to overfitting I am. All right, so, and the more predictor variables I have, the longer it's going to take to fit the model. Now think about dummy variables. Think about one-hot encoding. If I have, let's say, 50 states, how many dummy variables am I going to get? 49 or 50, depending on how you do it. And now I just took categorical data, the lowest level of data type I can have, and created 50 columns, one column to 50. Does that make sense? No, it doesn't. Is state a useful predictor? Honestly, yes, it is. It's useful in the project I'm working on right now. So binning is our number one. Our number one tool is that we're going to do binning. I'm going to take similar levels, I want to put them together, and my goal is so that on all of my dummy variables, I have approximately the same percentage of ones and zeros on each of them, approximately. So if I had 5 levels, ideally I would like 20%, 20%, 20% on each of them for ones, not zeros. Why is that? From an entropy point of view, equal proportions gives me the most, potentially the most informative that I could get, potentially. All right, so I want to bin so that ideally I would have, just better predictor variables. Now, if I know that certain levels are just going to perform very similarly on the target, I'm going to put them together. And honestly, I'm not going to really worry about the other levels at all. I'm going to use subject matter as my number one way of going. If I don't have subject matter knowledge, then I'm going to start relying on mathematics and that entropy point of view that I just told you a moment ago. All right, so by that, like, I don't know what's going on. I am not a real estate agent. I have never been to the area that, or I think I have been, but I'm not familiar with the real estate in this area. And so I can't really tell you what should be grouped together and what shouldn't be. I'm naive. I don't know. And at work, when I'm in this position, honestly, my subject matter experts are too busy to help me. So what I'm going to do, I'm going to automate some code to go through and group together so that, approximately speaking, as well as I can, I want to have levels with similar target variable average together. And I want to work so that we're going to have approximately, like 1/3, 1/3, 1/3. We're going to bin into 3 groups if I can do that. And so here, this is binning by similar target variable statistics. Now, another way to go is binary binning. All right, so in binary binning, I'm going to set a threshold. Above the threshold, I'm going to put a 1. Below the threshold, I put a 0. Now, this is a very, very, very coarse binning, but, and I'm using my conditional average for this. The reason why this is very nice is that instead of having 50 columns for states, I would just have 1. And with that 1, it's easier to do my feature selection, like especially early on in the process. And so if I want an easier way to do screening on variables, binary binning is a good way to screen out like your less useful categorical predictors. Now, this next one, this is coming from Morgan Wang. This is categorical smoothing. This is where we convert our categorical column to numeric by replacing the levels with the conditional average. So if I had states, I could say, hey, I'm going to take the average sales price in Florida is going to be in the place of Florida. The average sales price of Georgia in the place of Georgia. The average sales price in New York instead of New York. I'll do this for all 50 states. Okay, so now let's go ahead and actually do our data preparation. And so what I'm going to do is I'm going to figure out where do we have similar groups. All right, so on this first one, this external quality, you'll notice that almost 2/3 of the data is TA and 1/3 of the data is good. A small percentage is fair, a small percentage is excellent. Well, what would you naturally do? Well, you would put good with excellent. Now, fair could go with TA or it could go with the good, excellent group, right? Well, by using the sample average, I can see, you know what, I want to put it with the lower one, which is TA. So I've got two groups, FA, fair, and TA are together, and good and excellent are together. Okay, so I've effectively converted this into a binary vector. Okay, and so now we've got NA, fair, and TA are in one group, good and excellent are in another. All right, that makes sense. Now, central error is going to ultimately get converted to a binary. Now, for basement quality, we have NA, fair, and TA, once again, are all going into their own group. Good and excellent are going into their own. And you'll notice that this is end up being pretty close to 50-50, right? I mean, that's really close to 50%. Now, there's no perfect algorithm for binning. How I'm achieving this is I'm using cumulative sums in two different directions to be able to achieve like like where the cutoffs are. And I'll scroll back up to the code so you can see that. So how I'm doing this is that I have the cumulative sum of the proportions going, and then I have 1 minus the cumulative in the opposite direction, and then I take the average, and then I do cuts at 1/3 and 2/3. Now, there are issues with missing values because there are levels in the test set that are not in my training data. And in those cases, I just basically put it close to the middle, close, wherever the cumulative value of 0.5 is. All right, let's see if anything else. Garage finish, NA, unfinished, refinished, finished, stuff like that. So, we can go through, and honestly, this looks like it did a pretty good job. I didn't scrutinize this before the video, but I'm actually feeling, pretty good. Like we have basement and attached are going into the same bin. Built in is by itself in the high category. This is looking good. Now I'm surprised that detached is as low as detached and two type. I thought there would be more two type in there, but this is looking pretty good. Now, if you scrutinized it, there you would notice that I'm cutting here two types, and basement, if I look at their sample averages, they're pretty close. The sample averages would indicate that they should be in the same group. There is no perfect system for binning in an automated manner. You have to make subjective calls. This is a good place to start. If this was a real life project, I would go through and scrutinize my cut points all the way through. Also, when I go through and write this for my actual code for production, I'm actually going to set it up to do manual switching, manual binning like this instead of how I did it. I did it manually, but I would actually have code that says NA, carport, detached, two types, and so on inside my code to specify how it's going to happen. The reason why I do that is that it becomes easier to read. Like when I get my peer review or I have to look back at my code 6 months later, it's easier to figure out what the groups were when I look at the code. I don't have to bounce to an exterior table. All right, so let's go ahead and scroll down, keep on working through. And you'll notice I've got more and more values coming in, like neighborhood, grouping them together. All right, I think that's enough of that. So let's get back up. All right, so now that I've binned my categorical predictor variables, I'm going to convert them over to dummy variables. So the reason why I'm doing this is that scikit-learn cannot use any type of categorical data, strings, objects, categories, ordinal. It won't take it. You have to convert it to numbers in some way, shape, or form. That means either I have to do dummy variables with or without binning, or I could do categorical smoothing. I have to do something. And so here, I'm just going to go ahead and do exactly that. And so now I just went through and made the changes. So here you can see, here are my actual dummy variables as they actually were produced. They go across, I've got zeros and ones. One if it's at the particular level of the categorical variable, zero if it's not. All right, now I'm going to transform my numeric predictor variables to have a distribution more similar to normal, if that's possible. So classically, we use Box-Cox. Box-Cox is the classic transformation. It can only handle positive values, and it is very well understood theoretically. If you go and check out my theoretical linear regression videos, you'll notice that I talk about Box-Cox, in a couple of videos. So, very well understood theoretically. It's very nice. Proofs and all that business are available, but it only handles positive values. So what I'm going to do, I'm going to choose Yo Johnson instead. Yo Johnson, I can handle positive and negative values. And generally speaking, if it's all positive numbers, the resulting distribution tends to be close to Box-Cox. So I think it's worth it just to automate it. If I wanted to be a little bit more persnickety for the positive predictor variables, I would go through and consider both Box-Cox and Yo Johnson. All right, so mini supervised learning structure, like the variance of the column will make the column more or less influential. So like support vector machines is a good example of this. This can also be an issue with k nearest neighbors. K nearest neighbors, if I have one variable that spreads it, that has high variance, I can end up, basically partitioning on that one variable if it has much greater variance in all the other variables. And so this can be a problem in fitting, and that I'm not picking up the full signal. So to deal with that, I'm going to go ahead and subtract the column mean and divide by the standard deviation. All right, so why do I do this? Well, this puts each predictor variable on equal footing when I'm building models that are sensitive to predictor variance, such as k nearest neighbors and support vector machines. Also, this makes feature importance easier to interpret. Usually the output from functions take this into consideration automatically, but if you had to do things manually, like using like the coefficients from regression, this makes it a lot easier if I do the center scale aspect. Also, by having this center and scaling process, what this does is that this actually makes the columns unitless. And by being unitless, I have a better idea of what the extremes are. We tend to use the standard normal distribution as our benchmark of greater than 3, less than -3 as cutoffs of extreme. But it's much easier to visually spot outliers when I don't have to consider the spread of the data. All right, so to do this, I'm going to use scikit-learn. Okay, and so I'm going to use the power transform method, is Yo Johnson, which is actually the default, but I explicitly stated it to make it clear in the video. And now this creates an object by which I can transform future data sets. All right, so this is an object to transform data sets with. I have not transformed the data set yet, and I need to actually use the transform function to be able to do that. I need this if I'm going to be building a pipeline for future unseen observations. Similarly, I'll use standard scalar to subtract the mean divided by the standard deviation. The parameters for centering is mean equals true, and to scale to variance standard deviation equal to 1 is with STD equals true. All right, and so once again, this is an object for transforming unseen data, and then boom, I just go ahead and transform it. All right, so now let's take a look at the histogram of it. Now, normally I would go through, and if I was doing this for the actual stakeholders, I would, show these individually. Actually, I probably wouldn't show the transform plots. I would show the originals, but just to show you, the output that, here, looks like it's trying to be closer to normal. Definitely got zero inflation, trying to be normal with zero inflation. So there's some things to think about in the future. This looks like it did a good job of getting close to normal, close to normal, and so on. I definitely have things that look, if not binary, nearly binary, which might be something I want to address. Now let's transform our target variable. Many model structures, such as generalized linear models, neural networks, and linear regression will actually perform better if my target variable is not skewed. And we would prefer to have normally distributed if possible. That's not strictly a requirement, but symmetric is, generally speaking, symmetric is much better than skewed for the purpose of fitting models. Now, this will help me build a better model by model fit standards, but there's some disadvantages. First of all, if I transform my target variable, that means that my inference aspect is always based off of that transformed version, not the original version. So I'd have to extract the features of the transformation from the code, from the object, and then figure out what I was looking at to be able to, do like the pencil and paper mathematics on it. Also, after I get my predictions, I need to run an inverse function to convert it back to the original scale. So, there's some disadvantages here. All right, and so once again, I'm going to use power transformer like I did before, but here I'm leaving this on its own so that it's just the individual target variable. And, I do this so that it would just be easier for me to keep things organized and make sure I'm not, doing something unexpected where I have a mixture of the predictor variables and the target variable. I want the target variable to be very distinct. All right, and so let's go ahead and transform it. Now, something you will notice is that I didn't just go straight into sales price. All right, so what's going to end up happening if I just had sales price without this LOC and without the colon, without the comma, I would end up getting an array instead of a data frame. And so the scikit-learn function is going to throw errors, and this is how I got around it. All right, so here's a histogram of the original sales price, and here's a histogram of the transformed version. So if I step back for a moment, we can see that these two are definitely different distributions. Now, the difference between them is a transformation. This looks a lot more symmetric, and you'll notice that the transformer went ahead and centered and scaled the data for us. Very nice. And so here I was skewed right. Here I'm closer to normally distributed, looks a lot more symmetric. All right. And now one thing I want to do, I want to be sure that the inverse function actually works the way it's supposed to. So what I'm going to do is I'm going to apply the inverse transform to the transformed sales price. And then I'm going to subtract off the original. Okay, so then I'm going to get the difference. So I took the sales price, transformed it back, subtract by the original sales price. If the inverse is working and everything is perfectly accurate, I will get exactly 0 every single time. All right, so remember that when I do the subtraction, I'll have positive and negatives. When I work with those, I don't want to be dealing with positive and negatives, so I took the absolute value, and I took the average. So this is the average difference. And you can see that this is, scientific notation to the -10. All right, so that's small enough that that's just round off error. I'm not worried about it. I am convinced that for my purpose, they're the same. And then I save my data so I can use it. At work, I would store this in Snowflake, but I'm working on my personal computer for this video, so I'm going to save it as a CSV. All right, so we talked about a lot of stuff. Data prep, data prep, data prep. You need good data to build good models. You need good data to build good models. You need good data to build good models. Data prep is usually our first chance at getting good data. So this is my one good shot to be able to get my data into the best presentation possible to get the best models possible. Do your data prep, then your categorical variables. That's all I've got for you. Life is short. Do math.